Hi, I'm Rich with InsideHPC. We're here in Frankfurt at ISC 2015. I'm here with Gilad Shainer from Mellanox. How you doing, sir?
Good, I'm great. How are you, Rich?
Great, great. We're looking forward to Top 500, having a great week here. But, glad we're at Champions Sports Bar, and you guys are certainly the champions of low latency interconnect. I wanted to ask you, what is important to focus on in this new world, the latest technologies? What's going on with interconnects?
Yeah, I think integrates become more and more important, right? In the world of data and more data, it's important to be able to move the data faster so you can analyze the data faster, doing things in real time. It's important for HPC, but it's also become more and more important in other areas of data analytics, machine learning, and other things. All depends on moving the data faster and faster and faster. Now, in the interconnect world, there is like two architectures that people choose to implement. One kind of architecture is what it's called onload architecture. And onload architecture takes all the smartest out of the interconnect and pretty much runs everything on a CPU, runs everything on a software. Why? Because it's easier to build network devices, because they don't need to be smart network devices. Then because you can change protocols and create proprietary things and modify from generation to generation. Everything is done in the CPU. The other approach is what's called offload architecture, where you actually move things that are traditionally done in the CPU or in the software and run it on the network devices, in the network, in hardware. When you look into performance and scalability, right, that's what's matter. How do I increase application performance? How do I scale? How do I enable further efficiencies? Onload doesn't give you that element. Because in Onload, you're still running things on the CPU, things running things on the software. You create a lot of overhead on the CPU. You reduce the CPU utilizations to be to run more application cycles because the CPU needs to manage the network. The CPU needs to create data packets. The CPU needs to check reliability and things of that. There is a lot of things that the CPU does which is not related to the application at all. So reduce the CPU efficiencies, and you run things much slower than what you can. Um, Keylogic, for example, in the days where they did InfiniBand, this was their approach, and that's why Keylogic didn't really manage to take market share, because they didn't provide efficiencies or performance or the scale. Now, Intel acquiring the Keylogic InfiniBand part is maintaining the same architecture. Why? Because Intel does the CPU; it's easier for them to do that, but it doesn't give the value to the user. Doesn't give the value to the application side.
Yeah.
Okay. On the other side, we believe in offload. So moving things from the CPU to the network, that enables you to increase the performance of the application. That enables you to move things faster. That enables you to scale. And we see it in multiple evidence, right? We see it, for example, on the top 500 list, where we connect most of the systems in the top 500 are connected with InfiniBand. And the reason, because InfiniBand does give them the ability to scale, to achieve the performance, to run what they want to do. And on that architecture, we'll continue to invest. This is where we think that the path to exascale go through.
Okay, okay. So you guys have been using Offload from the beginning at Mellanox, and you've proven the scalability. I wanted to ask you about integration because the focus seems to be, is that the target?
Yeah, it's a good question, because there is a lot of people talking about integration and non-integration. Integration, it's not the target at the end of the day, right? We are not here to do integration. We are here to enable the exascale. So, taking a NIC device and a CPU device still connected with PCI Express and put it in one package and call it an integrated device as the target, it's not what you want to focus on. You want to focus on, how do I enable the next level of performance, right? And that takes you to look into not the integration as the target. You need to look on the data center as a whole. You need to look on the applications running in the data center itself, and look into, how do you take the data center to the next level of performance. And when you look on that concept, you understand that the only way to do it is with co-design. So working with partners and doing co-design between hardware and hardware, between hardware and software, and between software and software. For example, the project that we did with NVIDIA around GPU Direct RDMA, that was a co-design between hardware and hardware to enable the next level of performance. So we'll be able to cut application latencies 60-70% and actually achieve 2x performance on different applications. That's one example. Now, in a software and hardware co-design, the idea is to move things from the software to the network. And when you move things from the software to the network, you can actually make the next big thing. In the back few years, the big thing was moving from a single core to multi-core. Why? Because you get into what the most you can get out from a CPU. You couldn't increase the frequency. You could increase the frequency a little bit, but it's not making the big deal. The big deal was moving to multi-core, because now you can enable many more processes to run. You look on that from an application perspective. The same happens here. Right, so network devices today runs in nanoseconds. Mellanox switch runs in 90 nanoseconds, faster than anything else that exists out there. My adapter cards runs in less than 150 nanoseconds. So we're talking about nanoseconds here, and making the packaging or not packaging. You're gonna cut what, 2-3 nanoseconds? There is not much you can cut with moving to the packet to integration or packaging. Yeah. So packaging integration is not the target. The target is how do you go to the next level. The next level is that's what we do today with a large ecosystem of partners. Is looking into the data center and application wise, and looking into a complete communication scenarios, and taking those complete communication scenarios that runs tens of microseconds on the CPU today, and integration and packaging will not help you getting that faster anymore. Yeah. Moving those and map them on all the network devices. And once you move and map that to all the network devices in an offload way, you can take operations today that runs in tens of microseconds and run them in a single microsecond digit, 1 or 2 microseconds. This is an order of magnitude change. Okay, so now we're not talking about taking a 100 nanosecond device, have a packaging, and make it a 97 nanosecond device. That's not the big thing. That's not the target. The target is to map those operations, and will enable with our partners, will and the users that we're working with, will enable the next level of performance boost by changing or reducing latencies of complete operations in an order of magnitude.
Okay. Well, in these terms, then, when we're thinking about the whole system, the whole cluster, right? Flexibility and topology seem to me to really matter. Right. Because my application is not going to be the same as Brian's over there. It's going to matter how you do that. I wanted to ask you about flexibility in this approach.
Right, it's a good question. So flexibility is important. So standards, flexibility, open source, enable people to innovate. So that's why it's important. InfiniBand was designed by a large ecosystem to be the most flexible network out there. InfiniBand was the first SDN network, if we look on it. And InfiniBand switches, for example, support different topologies by implementing routing tables. So those are tables that map incoming data to where it needs to go out. And since those are open tables that are exposed, you can support any topology that you want with InfiniBand switches. If it's FAT-tree, or islands of FAT-trees, or toruses, or dragonflies, or meshes, or anything that's going to come in the future, you can support. And it's not only that, it's also exposed to the user. Yeah. So you can go in and change the routing yourself and optimize that to your application. This is where innovation comes. This is where performance comes. Proprietary protocols that we're looking at, or people try to invent, lack that flexibility. So we're seeing the new proprietary protocols coming out as protocols that cannot map to routing tables in the switches. And they are forcing users to go and use a specific topology because of lack of flexibility. Because they cannot support something else because of multiple reasons of issues that they need to deal with. And that's something that we don't believe that will take us to the future or will enable the next level of applications or creating new applications and flexibility. So Mellanox will continue to invest in what we do. Open, supporting those multiple protocols by having those routing tables, exposing that interface to the user, and enable the user not just to think about how to optimize the applications, but also how to build the next exascale system, which might be a different topology might support other things, and that's enabling not just ability to optimize now, but also to innovate in the future.